Go. All right. So the plan for the day, my friends, plan for the day is I'm going to entertain homework questions if you have them. If not, I mean, like, I can put that off for as long as you want because they're not my homework questions to do. You know what I'm saying? So if you have homework questions, I am very open to entertaining them. And then we're going to talk about the Rotational Acceleration Lab. I've got some write-up expectations to share with you. We're going to make a data analysis plan, then we'll keep collecting data. We'll get as far as we can with that. We'll reassess at the end of the period today to decide if we need a little bit more time tomorrow or if we're ready to move on. Does that seem okay? Yeah. Fantastic. Homework questions, things that you would like to discuss with me? Just going to open that up. I'll give you like a 30-second thinking window. Otherwise, I can ask that every day, and that's totally fine with me too. I don't care. Yeah. Chapter 8. Problem 20. So this one looks very similar, if I'm looking at the right thing, to the balance problem. Is that right? Okay. So let's take a look. So this is chapter 8, problem 20, for those of you that are... Okay. So it may make more sense to you now. I don't know when you started doing it, after you did the applied problem, because this looks very similar. So it says, I'll read it for you. It says, a thin 2-kilogram box rests on a 6-kilogram board that hangs over the end of a table. So here's your table. And here's the board. The picture looks almost the same. Oops, I need to make it a little longer on this side. Sorry, just so drawn not perfectly to scale, but a little bit more. And the box sits here. So this is a 2-kilogram box. The board has a mass of 6 kilograms. Hangs over the end of a table. How far can the center of the box be from the end of the table before the board begins to tilt? So it's a similar setup. It says that this distance here is 30 centimeters, and this distance here is 20 centimeters. And so now instead of moving the whole system, which is what we did in that applied problem, we're just going to move the box. And the question is, how far can I move the box before the whole thing rotates? Should we go through it? Yeah? Okay. So how do we start? What do we do? Torque net stuff, is that what you said? For sure. Yeah. Okay. So so we're going to say net torque has to equal 0. We know that, right? Because it's at equilibrium, so it can't be going anywhere. So the net torque has to be 0. I prefer, before I write a net torque equation, to know what forces are acting. So I would prefer to do what first? Yeah, let's draw some arrows on this, right? So what forces are acting on this system? Force of the earth acting on what? Force of the earth acting on the meter stick. And it's 50 centimeters long. So the 50 centimeter stick or whatever, I don't know. Where is the center of mass of that board?
It's the part that's right there.
It's going to be like right here, right? Yeah. It's going to be like right there. So I'm going to put the center of mass of my meter stick right here. And so I'm going to say that's the force of the earth on the board. Okay? And that's acting 5 centimeters from the edge of the table. Does that make sense to everybody? Okay, that's one force. Any other forces acting on this system?
Force of the earth on the weight.
On that box thing, whatever that is? Yep, and we're assuming that it's a pretty uniform box. I'm not drawing these arrows to scale. I'm just trying to get them into the whole picture here. So this is the force of the earth on the box. Okay, so I might call this F, oh my goodness. FG1. I'm going to call this FG2. Any other forces acting on the system?
Yeah. There's a normal force at the edge of the table.
There's got to be, right? If your inclination was to say, nope, there are no more forces, then look what's going to happen. You've got two forces pulling down. Where would the system go?
Down.
Right? So there's got to be something. And we're saying that very little teeter-tottery point. So we're going to put that force right at this edge here, right? That's the force of the table on the system. Maybe a normal force we can call that. Okay. So like we got those three forces. So we got our forces drawn. We need to pick an axis of rotation. You can put it wherever you want. Does anybody have an inclination of where you would like to put it? There's one really good choice and then a few, or I guess an infinite number of less clever choices. Not to say that you can't do it that way. Edge of the table is the best choice. Why is the edge of the table the best choice? It makes the torque of the normal force zero, and that makes our life better. So that's what we want to do, right? We want to make our life as easy as possible. So let's put the axis of rotation right there. So then, when we write our torque net equation, we've got the torque of FG1 plus the torque of the normal force plus the torque of FG2. So that's going to be the force of gravity 1 times the radius for that one, plus the normal force times the radius for that force, plus the force of FG2 times the radius for that one. And that all has to add up to 0. What's the radius for the normal force?
0.
0. So that means this whole thing goes away. See ya. We know FG1 is going to be, what is that going to be? That's M1G times, it was 5 centimeters. So if you wanted to put, we could put that M in there if you like your numbers. What was it? What was the mass? I don't even know. 6? 6 kilograms. And then I've got that plus 2 kilograms times G times the distance that we don't know. That's R2. Those two things have to add up to 0. How do I get two numbers to add up to 0? What do I know about one of them? One of them's got to be negative, right? Which one is going to be negative in this case? It doesn't really matter, does it? But if we're rotating about this center point where it's yellow, we come down this way. That's if it was just this thing, it's going to pull down this way. Is that positive or negative? Negative acceleration, right? Because it's clockwise, so it's negative. So I'm going to call this one the negative one, just so we're going to use our universal truth. But you could call that one negative, and in terms of your answer, it does not matter. It's just one or the other has to be negative. But again, trying to kind of stay consistent, I'm going to make this one the negative one, which basically says that I've got 6 kilograms times the acceleration due to gravity times 5 centimeters has to equal 2 kilograms times the acceleration due to gravity times some unknown number of centimeters. Oops. G's are going to go away. Can you figure out what R is, even without a calculator? What is it? We got 30 on this side, 2 over here, so it's got to be 15. Yeah. Problem like this where we're just kind of trying to do it and it's kind of, for our happiness's sake, I'm not going to worry about it. But you do want to read questions carefully, because sometimes when it asks a question, it'll say, where on the meter stick, like where are you going to place it? So you have to make sure that you're saying 15 centimeters from what? Because is it 15 centimeters from the end? It's 15 centimeters from the edge of the table, right? So I would strongly encourage you, as you're practicing problems like this, to get into that habit of saying 15 centimeters from the center of or from the edge of the table or whatever, just so that you're identifying a specific location. Okay. Other homework questions that you have that you'd like to go over? Did you have one?
Yeah, chapter 8, problem 13.
Problem 13. Sure. Oh, yeah. Okay. Chapter 8, problem 13. So it says a uniform beam of length 1 meter and mass of 10 kilograms is attached to a wall by a cable, as shown in the picture. The beam is free to pivot at the point where it's attached to the wall. What is the tension in the cable? So we've got a wall over here, and we've got this beam that's sticking out, and it's got an axis of rotation here. So if left to its own devices, it's going to fall, right? But we have a cable or something that goes to the end and is holding it up. Okay. Why do we have this situation? I don't know, but it's a fun little physics problem. So we'll do it. So this is 30 degrees. This thing right here is 1 meter. And what else do we know? We know that the length is 1. I just said that. The mass is 10 kilograms. And we want to know FT. All right. What are we going to do? Go, Nick. The torque net equation, right? It's like the mantra of all of this, right? Torque net. And indeed, what does torque net need to equal? 0, because it's at equilibrium. So it's got to be not going anywhere. All right. So if I'm going to write a torque net equation, first of all, I need to know some. Indeed. So let's draw some forces. So what forces are acting in this system?
The earth on the moon still going to assuming it's constant.
Like here? Okay. So the force of the earth on the stick, Fg. Okay. That's one force. One force doesn't give us a torque of 0. That's for darn sure. Any other forces acting on that system?
Tension.
Tension, since they're asking for it, probably exists, right? For sure. So let's take a look. Let's put that tension in. Where's the tension going to go? Along the rope or along the cable, right? It always does. From the object along the cable. So it's going to go up like this. F of the rope on the stick. Ft. Okay. Any other forces acting? Go ahead.
No, not exactly, because the force need to be perpendicular to this.
Well, I'm just drawing the forces that are acting, right? So gravity forces always pull straight down to the center. Tension forces always pull along a string. I think we're going to have to break it into some pieces, yes. So I think absolutely we will, but let's get all of the forces drawn first, and then we'll do that. Is that all the forces that are acting? Is the system at equilibrium? It's not accelerating, right? Yeah, so it's not accelerating, so it's at equilibrium. That means that the net force acting on the system needs to be what? 0? Yeah, you can say it with certainty, not with a question mark in your brain. Yes. So if you've got a net force of 0, let's look at the forces that are acting here. Right now I've got one force pulling down and one force pulling up. Is that going to add up to 0? So, Razan, were you going to say something?
Was going that way to come out with left force or idiot?
Yeah. So, Razan's suggesting that maybe there needs to be a force this way. Is that what you're saying? Yeah, because I'm kind of combining all of your ideas. So Razan says there's got to be something here. And the reason for that, Nick had said that there's going to be a force up this way, right? But there's also got to be some of it in this direction. You with me there? So some of it goes up, some of it goes over. If there's some going this way, we got to have a net force of 0. So that means there's got to be a force pushing the other way. You can think about that if we got rid of the wall, all of a sudden, poof, it's gone. Is this thing going to stay at equilibrium? No, it would swing this way, wouldn't it? Yeah, so it's not really at equilibrium until we have that other force acting. So we've got to have another force acting in the horizontal direction. It is a normal force, yeah. So I'm drawing it kind of from a yucky spot, but I'll just do it there. So the force of the wall on the system, that's an Fn. Yeah. So now if I add these three forces up, I feel like I can actually get an F net of 0. Okay. Okay. So we got a bunch of forces. Now, what are we going to do now? What did you say? It was kind of a snarky comment, I think, but I'm not sure. All right. I mean snarky in a nice way. We can write down our torque net equation, right? Once you've got your forces, you can write down your torque net equation. So let's do it. Every force has a torque associated with it, right? So I've got the torque from the normal force. I've got the torque from the gravitational force. And I've got the torque from the tension force. Okay? Where's our axis of rotation going to be? Don't make your life too hard. Do we know everything we need to know about this one? We know where it's applied. We know how big it's going to be because we know the mass and the acceleration of gravity. We know everything about this, so let's not get rid of it. Right? It's all stuff that we know for the force of gravity. Do we know everything we need to know about the force of tension? No. So should we get rid of it? Well, it's what we're looking for, though, right? So it's like one of those things, if this was the thing you're looking for, then probably not a good idea to get rid of it, right? That's going to kind of defeat the whole point of doing the problem. So let's not get rid of that one. Do we know how big the normal force is? Do we care? No. So where would be a great place to put your axis of rotation? Right there, right? Let's do it. All right, get rid of the stuff you don't care about. Isn't there like some sort of philosophical something about, I don't know. Yeah. Anyway, we're going to make it a thing. Force of gravity times the radius for that force plus the force of tension. And Nick's going to disagree with me in just a second. I want you to, so hold on to it for a second. Times the radius for that tension. Is it the entire force of tension that's causing a torque? No. What's the difference? Jasmine, are you? Yeah.
It's the perpendicular component to.
Right. It's only the perpendicular part. Right. So that has two pieces. So we've got one part that goes straight up. FT Y, we'll call it maybe. And this part goes over here like this, FTX. We only know or care at this point about the Y part. So this is going to be FT times, okay, oh man, woo! Got some triangles, we love the triangles. If this is 30, that's got to be 30? Is that okay? Opposite interior angles or something like that, isn't that what it's called? Yeah. So that means FTY is going to be FT times the sine of 30. We feeling okay about that statement? How far away from the axis of rotation, noting that we put the axis of rotation right over here at the wall, how far away from the axis of rotation is that tension force being applied? 1 meter. And then we've got, I guess we can just add it in this color. Here we go. So we got the mass of the stick times the acceleration due to gravity times the radius, in this case, is 0.5 meter. Two things that I'm adding up have to equal 0. What does that mean? One of them's got to be negative. One of them's got to be negative. Which one's negative? This one here. If my axis is here, this one's going to pull it down clockwise. that's got to be my negative one. The force of gravity is going to be the negative one. So here we go. So we've got Ft sine 30 times 1 meter. That's an easy thing to multiply by. Is equal to the mass of the stick was what? 10 kilograms times acceleration due to gravity times 0.5 meters. Does that get you where you need to go? So using Gunner's shortcut, we're going to say G is 10. So that makes this 100, which makes this 50, right? So it's going to be 50 divided by a sine of 30. Okay. You got that. All right. Other homework questions? Anything else you got for me?
Do you have to do the lab stuff?
Are you talking to me?
Yeah.
What do you mean? We've got more stuff to do after this. Yes.
No, Henry, we're just done. We're leaving.
Any more homework questions? Last chance, friends. We're done. I'm asking, do we have any more homework questions? That's all I want to know.
No, not today.
Fantastic. Okay, let's move on, shall we? Yes, please. All right. Weird tension there. We didn't need that. All right, we're going to start with the write-up expectation. So this is I told you guys this is a big lab. You've kind of gathered that this is kind of a big deal lab, right? This is a big, chunky one. I really want you to understand it. I love this one so much. So here are the write-up expectations. And I will post this up on Canvas so you've got it as well. Once you've collected your data, it doesn't have to be Excel. That's old. It can be Google Sheets, sorry. You're going to work together on your Google Sheets document, okay? You'll need to include well-labeled data with units. You'll need to include things like using average, make Excel or make Google Sheets work for you. Don't plug it all into your calculator and then type those numbers into the computer. That's a waste of your time. If it's been a long time since you've used Google Sheets and you don't remember how, and nobody in your group remembers how, then talk to me and I'll help you. I want you to learn how to do it. We're actually going to do some of this right now. You will need to come up with a clever way to graph your information. This is it. This is the physics right here, right? With some labels.
My chart, yeah.
Best fit line, that's a poor choice. An equation. And then calculate your predicted slope and percent error. Okay? In order to do these bottom three things, you really have to understand this system. And we're going to talk about that in just a second. Okay? One Google Sheet spreadsheet per group. I just need one. But make sure everybody's name is on it. That is due by next Tuesday at 11:59 p.m. Okay? So it needs to get to me by then. You've got time. I don't want you to stress out about it. I want you to do it right and do it well. You will need to do, please stop talking. You will need to do a conclusion evaluation section individually, and that's all still up on Canvas, but I'll remind you about what that looks like, right? So that's like, how did you do? Tell me what you found. What could you have done better? That kind of stuff. So keep that in the back of your mind as you're doing your lab so that you are making kind of notes like these are things that we could improve. Now, don't intentionally hijack your experiment so that you have things to describe. We could have done this better because we could have done, like the things we should have done. Like that's not a good plan. But I just want to let you know. And that's going to be due next Friday. So not 2 days from now Friday, but the first Friday of trimester 3. Does that make sense?
Yeah.
Okay. So your task right now, the first thing that I want you to do is with your group, with your lab group, you need to sit down before you get any equipment. And I would like you to figure out, and this may take all the rest of the period, and that's okay with me. I want you to do it. I want you to struggle with it, and I want you to get it. You need to tell me what you're going to graph on your y-axis and on your x-axis to get a straight line, and then you need to be able to tell me what the slope is. What the slope represents. Okay? I would strongly recommend that this involves some torque net equations, that this involves some F net equations, that this involves some kinematics. I want you to think it through so that when you go through and get your data, you understand what you're doing, okay? So I want you to get into your group, talk about it, get some whiteboards out if you need to. Stay in this middle part without getting equipment out so that you've got a space, right? Maybe group 1, 2, 3, 4, 5, and maybe 6 at the back table right there, okay, or something like that. Work on this. Check in with me once you think you've got it, okay?
I did it.